This is the Coasts and Beaches lecture. Of course, I'm going to start, as always, by sharing my screen with you. Remember that we're going to be working off of the mini lecture. There are always two lectures. I just like to keep every week saying the same thing in case somebody forgets. You have the main lecture under the Content tab, again titled Coasts and Beaches, and you have the Coasts and Beaches mini lecture in the folder for this week. Up until now, and I guess I'm biased about this material a little bit, but up until now, we've been covering very specific oceanographic topics, everything from plate tectonics through atmospheric and ocean circulation through waves and tides. They've all been pretty straightforward physics lectures, chemistry lectures, geophysical, geological, a little bit of biology, but not much thrown in. This week, I believe, is the first week that we're going to have material that includes the anthropogenic component of ocean. And that's not necessarily a good thing, okay? But it's reality. Anthropogenic, for those of you that don't know that term, is just a fancy way of saying man-made. We live on the coast. We vacation on the coast. We go in the water. We take boats in the water. We travel across the water to get to places. We use the water for shipping lanes. We mine and search for materials in the ocean. We build oil platforms in the ocean. We literally build cities on the edges of where land meets water. So clearly, the ocean and its coastal zone is impacted by mankind, by human use. The coast, unfortunately, then becomes the single most impacted area of any oceanographic setting simply because it's the easiest for us to get to. So we start first by talking about where beaches, land meets water with essentially small pieces of particles, right, that we call sand or rocks or cobble. We begin there, but then we're going to, in the remaining portion of the course, we're going to take it a little further offshore. But believe it or not, even when we're out in the middle of the open ocean, we do come full circle and realize that the vast majority of our impacts do become on the coast. This lecture is going to focus in two parts. First, we're going to identify what a coast is, look at a bunch of different coasts from all over the world, give a whole bunch of definitions for how processes affect our coast, and then we're going to look at some anthropogenic change at the coast. Okay, so classic textbook definition of a coast is a temporary junction between land and sea. In other words, it's not a permanent place. It can be edited and fixed and carved. It can be eroded away during a storm or just over regular periodic change after years and years and years of, for example, waves hitting a shoreline. It can be accreted or built upon. And of course, it's subject to change. There are a lot of processes that will occur, that change, some more dramatic than others. For example, a plate tectonic activity, of course, an earthquake might open up a section or cause a chasm, which could put a coast in a place that it had never been, for example, at a transformed fault line. Things that are a little bit longer in their processes to occur, like a biological process, can actually show that you can have different coastal zones that are living, that are biologically living. And we're going to look at a bunch of pictures that show all these different things. What you are going to notice, of course, is that at the coast, not only is it a temporary junction, but the position to which the coast meets, in other words, where the water meets the land, that position always changes, just of course as sea level does. Okay, so here could be a picture of New York City, right, which would be a city we'd be more familiar with. Instead, we're using Sydney, Australia. But what it literally shows us is that a coast doesn't have to mean the beach. It literally, by definition, means anywhere where land meets water. Okay, and in this particular coast, the water has to be salt water from an oceanographic perspective. Okay, you could have a lake coast in a freshwater system, but in oceanography, it's going to be any area where water with salt meets land. It can be man-made or it can be naturally occurring. So more often than not, people flock to the coast. People like to live in these settings because we like to recreate there as well. But by and large, the reason why we live more coastally is because shipping freights, goods, and services are easier to get in ports. Ports occur in coastal zones, so you have more manufacturing, more jobs, more industry, and people, of course, live in those same locations. It's a 1-2 punch though, because in doing that and in needing all of that stuff at the coast and then living in that same location, we cause a lot of damage to it. So our first picture was one part of Australia, right, which certainly looked like a built-up city with water around it. Here's the second part of Australia. Similar to, for example, if we were to look at New York City and where water would surround it versus if we were to go to Jones Beach or Jamaica Bay, okay? There can be coasts that hit different land masses at any given time. So in this particular location, this is more of what we call a quintessential beach. And this particular beach, of course, is sandy. Sandy beaches are not the only kind of beaches, though, which means that beaches are not only one type of coast. A coast can be a sandy or small-grained sediment area, or in this particular case here, cobble or large-grained sediment. It could also be muddy, loamy. It can be covered with grasses and materials. And so, of course, I want you to realize that a coast literally can be anything, anywhere in the world where land meets water. So there's no visual expectation in this lecture as to what a true coast is. Here's a classic example of a biological coast. This is all living. Okay, mangrove swamps in the southeast United States, think Everglades. They would have a similar setting to a picture like this. What this is showing us, of course, is a living biological mat that produces the ability, of course, for the floor to rise up out of the water. But of course, at high tide, water spills over and fills in this space. So this area is a robust biological community, but not necessarily one where you want to go and lay your towel. Okay, so different coasts have different advantages and disadvantages for recreation versus those that are good for storm protection. For example, this would be great for storm protection, but not necessarily for you to go and have a day at the beach. So coasts serve multiple purposes as well as look visibly different. Unfortunately, sea level, of course, plays a significant factor into where coasts are. Okay, so remember all the way back in section 1, we talked about the Wisconsin Ice Age that ended right around 21,000 years ago. So this is a little newer, meaning closer to present day. And it shows you where the edge of where the water meets the land or the coast used to be. In other words, if we were to fly to Florida and go to, let's say, Clearwater Beach, I think that's somewhere right around there, or Naples, for example, or anywhere on the Western Panhandle, right now, this is where you would go to lay your towel. 18,000 years ago, you would have laid your towel out here. Miami, though, then and now is roughly in the same location. However, we know that sea level is rising, and if sea level is rising, then the water is going to cover the green parts because the green is supposed to represent land. The water is going to cover the green parts, and as sea level gets higher, we believe that approximately, within the next 50 to 100 years, this could be our coastal vision. So cities like New Orleans, notoriously coastal and always hit by storms, already been submerged multiple times, and Miami, which sort of held ground for that 18,000 years to present day, as well as all the Florida Keys and about half of southern Florida will all completely be underwater. So sea level, in addition to how we alter our shoreline, in addition to the natural processes of where the water meets the land, all are going to impact our coastal zone. Beaches are our most classic coastal feature. Okay, a beach is technically a zone of loose particles that covers part of the shore. Fancy textbook definition: area of accumulated material, usually sand, moved by action of waves and currents. So we know how waves operate with refraction. They bend toward the shore from our waves lecture. And we know how currents operate from our ocean circulation lecture. 4 currents make up a gyre, clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. And of course, if the water is moving, the material that they move, which would be sand, moves with it. So if a current is moving in this direction, sand gets deposited on the beach. If a current is moving in this direction, sand gets deposited on the beach. Have really big waves, you erode away the material. Really big waves erode away the material. It's a loose collection. So again, changing. always, always changing. Now, if you're a rock, it's a lot harder to move you than if you're a grain of sand, right? So of course, that loose particle, the size of it, is going to make a huge difference as to how stable our beaches are. Here is your typical beach profile. If you were to take this course in the spring, and we were live and in person, we actually go to the beach and we do a beach profile. Because we are doing remote learning, and actually Suffolk has gotten away from requiring field trips. Because of that, we're essentially going to bring the beach to you. So in Lab 9, you're going to watch a series of videos that take you all over the world and show you what the sand, the sediment, and the coast look like. We're also going to take you on a video to the North Shore of Long Island and the South Shore of Long Island and explain how they were formed, and then give you a close-up of what those areas look like. A typical beach profile of the South Shore on Long Island typically looks like this. What's interesting is the only time that you see the word beach is here, okay? The rest of it is called a berm, a dune, or a bar. From a waves perspective, here's our marching soldiers. And you guys now can see that the wind is obviously coming from this direction because the white caps are causing it to move toward shore. We know we're going from an area of deep water to an area of shallow water. So we call those two areas in the deep water the offshore zone, and in the shallow water, the nearshore zone. We know that because that's where the breakers are, right? Remember from the waves lecture, we call that the surf zone. So you have a series of locations on your typical beach profile. Now what we've done is we've overlain the waves lecture on our coasts and beaches. Notice that the berms get progressively higher as you move away from the water, and eventually that berm gets vegetated. That's going to be in the area that's typically not ever underwater except in an extreme storm event, and we call those areas the dunes. Again, typical beach profile, typical coastal profile when you have small sediment like sand. There are, of course, other types of beaches, right? Not just small, loose sand. You can have larger boulders, larger cobble like our North Shore. You can also have cliffs, permanent dunes, and then artificial beaches where seawalls have been built. So you can have vertical structures that actually manipulate how wide your beach can be. And if that happens, you're going to have a lot of erosion along this crest. And so you don't get typical higher in elevation and then vegetated beach profile. Remember in the last picture, you had a berm, another berm, and then a dune. Here you have no vegetation whatsoever, only one berm. And then you have your near shore, which again is the same as foreshore, and offshore in the same way that you did. But look how much closer that longshore bar is. This again, still a beach profile, just a different beach profile because we have manipulated the shoreline, whether it be naturally or unnaturally. Sometimes those steep walls can also give you sea cliffs or sea arches. This is a typical coastal California view. It does, of course, still give you some exposed beaches, but those beaches are few and far between. They're usually hard to access. And the sediment that's there is literally from the material that washes up as our marching waves approach shore, and refraction dumps it in these little nooks and crannies. Another classic picture of a same California beach or any location that has rocky cliffs. If you were to go and do the beach profile, and again, instead we're going to be doing it for you and you're going to be looking at the material, you're going to notice that the steepness of the beach is going to change based on season and storm. We're going to have it steeper in the winter because of erosion, and we're going to have it flatter in the summer because this is where it builds up. Another word for that is accrete. So your typical beach profiles not only are going to look different on a season by season basis, but on a sediment by sediment basis. So your swell profile represents your summer profile. Look how wide and gradually sloping that is, okay? Your storm profile represents, again, an area in a storm when there's going to be erosion, and your winter profile. Look at that. No space, or only limited space to lay your towel, as opposed to the summer when you have this much more space. Offshore bars, of course, are where the sediment is going to land. So all of that material that eroded away lands in the offshore bar. In the summer, this material gets pushed back up on the beach, and you end up with an accretion and erosion process. Say those terms a couple of times fast. In other words, the beach profile gains in the summer and is lost in the winter. And if not manipulated, will continually and constantly do that. So the same sediment will move from the offshore bar to the beach and from the beach to the offshore bar each year. Unfortunately, we typically go and dredge our offshore bars so that boats can get through, or so that we can beach scrape and manipulate our beaches every summer. So by and large, we end up with an erosion event over the long term. Beach profiles, therefore, are going to have a couple of hard and fast facts. Steepness is going to depend, again, like it said, based on season, whether you're in winter or summer, and if you're an erosion or accretion event, and on sediment size. So you're going to notice along the North Shore that we have an increased sediment size, and this is on Long Island, and on the South Shore, you have a smaller sediment size, similar to sand and cobble. So if you have a larger sediment size, your beaches are going to be steeper. If you have a smaller sediment size, your beaches are going to be flatter. So our beaches are flatter in the south and steeper in the north, again, on Long Island. Here's a typical average slope for our different sediment types. So we are increasing in size and therefore increasing in slope. Okay, so that would be North Shore, where the arrows are going, and then South Shore covers our sand. Beaches therefore exist in a delicate balance between gaining material and losing material. Accumulation, again, means to accrete, and destruction means to erode or erosion. Waves, just as we said, can certainly transport material onto the beach or to the offshore bar. And now the second part of this lecture is going to give you the second half of that delicate balance. It's going to explain a new term called a longshore current. Instead of putting stuff on the beach or in the offshore bar, this is going to go along the coastline, just like the name applies. Longshore, along the shore. Sometimes you even hear it called a longshore transport. Here's our refraction that we know back from our waves lecture. We always want to remember that our waves want to march in like the perfect little soldiers that they are, but they're going to bend or refract based on the coastal shoreline, and they're attempting to deposit sand on the beach. That would be an accretion or a gaining, okay? However, if the shoreline is running parallel, the longshore current, which runs parallel to the longshore, will ultimately move the sediment, in this particular case, to the right. If this were Long Island, then this would be toward the east. Ultimately, the east can't go on forever. If we moved all of our material from west to east along Long Island, what would happen when you got to Montauk? You would have no sand. So the longshore current can make or break us, and we've actually learned how to manipulate it so that we can keep our sand, but that has come back ultimately to bite us because we've manipulated it too much and caused a loss of sand. And that's what we're going to be discussing in the second half of this lecture. The longshore transport, remember, again, it's the wave refraction moving toward shore, always goes parallel to shore. So in the example you had before, shore was a parallel line, longshore transport was a parallel line, right? Here, the shore is not parallel, it's bent, so the longshore transport bends with it. Ultimately, it's telling us that sand is being deposited. Then it gets lost and gets deposited. Here, it's a high steep point. There obviously is something it's hitting on this side, so we end up with a feature that we learned about in section 1 of the course, a submarine canyon. Again, all of this is intended to show you that coasts are dramatically different all over the world, but the process to which they are made is always the same. On the west coast of the United States, you're going to see that that longshore transport is hugging the coast. But it ultimately results in these deep chasms, these submarine canyons, and then you have a net loss of sediment. On Fire Island, or any barrier island like we have on Long Island, it actually acts as a protective barrier. Instead of having the longshore current running here, where it can cause erosion and that sand would all get pulled away and lost, instead, this barrier acts as a barrier and literally moves the longshore current offshore. If it's moving it offshore, then that means you have less erosion in all of our bays and it protects us. So barriers are good. They act as a protective mechanism, moving the longshore current or the longshore bar further offshore. East coast of the United States, here's Long Island. You can see that our typical longshore current runs from north to south. So again, we have an erosion from Maine and a buildup of material in Florida. But then, of course, it has to come around the edge. On the west coast, we go from Washington to Mexico with the longshore current running in the same direction, again, from north to south. Ultimately, what we're looking for with our longshore current is an input and an output for a net steady state. Unfortunately, the two parts that make up the steady state, accretion or building up, erosion or loss, never end up equal. So we actually end up on Long Island in particular with more of an erosion situation because we've manipulated the shoreline. So we try to gain more of an accretion. So we ultimately, that's the purpose, that's the goal, is to get to a steady state. Okay, the second half of this lecture, as titled here, is going to be how we messed it up. Okay, human impacts on the beach. Now that we know about longshore transport and we know about waves, and we know that using longshore transport to our advantage and knowing where waves will move the sediment, we actually attempt to save the beaches, but really save our property, by manipulating the transport itself. For example, if we know that our shoreline is moving from the left to the right, okay, our longshore current or our sediment is also going to move from the left to the right, okay? What if your house is here? That means that it bypasses you. The sand goes right past. You end up with, let's say, a beach that's this wide, okay? Well, what if instead, here's your house, okay? Here's your current. We're going to call this your current beach, okay? What if that's not enough for you and you don't want the sand to keep moving? What could you do? What ultimately makes it stop at the end? It's when you have a perpendicular coast or something artificial that would stop it. So what if you built a wall coming off your property to bisect or intersect the longshore transport? What would happen? The long transport would come in, hit against the wall, and dump the sand in front of your property. You now would have, here's your house, not only the beach face that you had presently, but you would gain property. People said, wow, isn't this a great idea? This makes more sense. I get a wider beach. My house is further away essentially from the water. It keeps me protected during storms. Ultimately, that's a good idea. But what happens if your house is here? You end up with no sand, and your house literally has water right up to it. Unfortunately, that's what happens. You have severe erosion, either from natural storms, from the loss of the width of the beach, or from too much building up in coastal zones. Even worse is if in an effort to protect your house, you build a structure perpendicular, you then end up with a total loss of the beach, either on this side or this side, depending again on which way the longshore transport is moving. Erosion is not a good thing. In the example that I gave, where we were drawing the arrows from the left to the right, we said what would happen if everything moved on Long Island from west to east. Everything would get pushed toward Montauk, and then we would have no more sediment. Well, in reality, what happens is it's in the exact opposite direction. Why? Where was the longshore transport along the entire East Coast? Remember, it was coming from Canada and coming straight down, correct? So as it comes down from the north, it loops around us and then goes from east to west all the way along Long Island. Long Island is pretty much a straight line, and we have a lot of barrier islands all along, pushing that longshore even further out, so it's in even deeper water. Now, ultimately, that seems good, but really, what does it mean? I'm going to clean this picture up for you. What it ultimately means is that we're going to take all the sediment that we find here on the tip of Montauk, right where our famous lighthouse is, erode that sediment away completely to the tune of about 300 feet of sand, and we're going to give it to New Jersey. We're going to dump it in New York Harbor and ultimately land it on Sandy Hook. See this little hook? Clean this up one more time. You see this little hook sticking out? That's from the buildup, and that's Jersey, by the way. That's from the buildup of all of our sand. It's also why New York Harbor has to constantly be dredged, right? We have erosion from the Hudson River and a lot of material depositing there, and all of our sediment getting slammed in. Ultimately, though, what it means is it causes massive erosion, especially on the eastern end of the South Shore of Long Island. So the littoral transport, or again, the along-shore drift, is not our friend on Long Island. It's going from east to west. Any of you interested in being a coastal engineer? This is a fascinating subject to study. People spend their entire lives trying to find a way to stop this process from happening, because look at the loss. We do not have erosion, we have erosion, right? 600,000 cubic yards per year is lost from this process. So, since we have such massive erosion, and since the properties and beaches on Long Island are worth so much, and since we have so much infrastructure, we can't help ourselves but try to manipulate it. So again, that's why this half of the lecture is called How We Messed It Up, right? So just like I gave you the examples of drawing the perpendicular lines before, here's your longshore current, okay, in this case moving from west to east. If you take that longshore current and you bisect it, what's going to happen? You build up on one side, but as the example I gave you, the house on the other side is at a loss. So what's that house going to do, right? That house is going to build a longer wall. And then what happens? Hits here, bounces back. Now this gains, and this has an even worse loss. So more often than not, you get something called a groin field, multiple groins in a straight line, all parallel to each other, one slightly longer than the one before it, because each property is essentially trying to get out as far as it can into the longshore drift to capture or accrete as much sand as possible. If you put two groins side by side, we call them a jetty. Okay, so again, here's the terms: groin, jetty. A jetty can, doesn't have to, contain this little sort of hook. All that does again is allow for the material, for the erosion to get pushed around, right? For the longshore current to get pushed around. So the erosion gets dumped on this side and you have an even greater buildup on this side. We do this a lot with inlets because there has to be navigable, where boats can go through, navigable water in this location. So it's really important to keep those dredged, to keep them deep. Building these types of things like jetties in this particular location lessens the amount of time you have to dredge the inlet. Instead of going perpendicular, we can go parallel. Well, if here's our longshore current, we can build a breakwater parallel to the longshore current. This functions in the same way that a barrier island would. And look what this does. Build up and loss are equal. Here you have a steady state. But if this is your house versus this is your house, you're not happy. So that doesn't solve the long-term issue. Again, if you're building in these zones. Another example, so that was our third example called a breakwater. Another example is called a seawall. A seawall can run parallel or perpendicular, but it essentially, just as the name implies, excuse me, is a wall that is engineered, okay, where the water meets the land, or where you want the water to not meet the land. You put gabions or riprap in front of it, which is a bunch of little rocks essentially. These function as a lessening of the force, right? They sort of absorb the energy as the water hits the wall so that the wall doesn't get cut out from underneath and fall down. The energy gets absorbed by these rocks instead. And then not only is there a wall, there's a perpendicular component, which may or may not have a road or a structure, to shore it up, to make it even stronger. The problem with this, here's our marching soldiers. What kind of energy do they have? Disturbing force, all coming in. What's it going to try to do? Restoring force is going to try to put it all back. So the erosion becomes underneath. Instead of eroding the actual beach on the other side where your house would be, you undercut the sediment underneath. Ultimately, this wall will fall down. So the wall needs to be really deep cut in, or eventually this will fail. So all you did, right? You can never win against the ocean. All you did was move the problem somewhere else. So those are 4 examples: groin, jetty, breakwater, and seawall of how we've messed up the shoreline, how we artificially manipulate the shoreline. Okay, here's 2 that we've just covered, again, giving you the same visual and explanations as to why we'd want to have it. The final one is a simple thought process. Imagine you have some offshore bars out here that came from sediment that was here, but that got deposited in the winter. Well, we think it's our sand anyway, right? So why not go dig the sand pile out and deposit it back on the beach so that next year it can just erode away and end up back in the bars. They call that beach nourishment. And this is what we do often, okay, and it's permittable all along the south shore of Long Island so that our beaches are wide and flat in the summer and so that they can collect your $20 per person every day all summer long and you have the best beach experience. Ultimately, all it does is just put it back in the space it came and the next year they collect it. Of all of these examples, this is the most environmentally friendly, but it's also really expensive and lasts the least amount of time. So it doesn't seem to be an option that most homeowners or even beach community owners want to utilize because you have to do it too often and it costs too much, even though from an environmental perspective, it's your best approach. So let's take a look at what some of this material does and what some of these structures can do by looking at some examples all along Long Island. Okay, so again, terms you've heard already: groin or jetty. Rock revetment is the same as the riprap that you saw on the seawall. Beach scraping is the same as sand renourishment. That's the most natural. And a bulkhead is the seawall, just doesn't have necessarily the riprap. So you're familiar with all these terms. Ultimately, what we're trying to do is allow for a natural berm, dune. If we could just allow for a natural setting of a natural beach and our typical beach profile look like this, we'd have a natural way to accomplish all of these. But we don't have enough room on Long Island to do that, so instead we go with these processes. So let's look, and I apologize that some of these pictures are a little grainy. Some of them I've taken from USGS, and so when I blow them up into the PowerPoint, they get a little grainy, but you get the point, right? House, 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 house. In other words, a really built up, like Fire Island, a really built up coastal zone. They live way too close to the water's edge. Well, this house probably built a groin. Look what they earned. These houses are happy. These houses are mad. So you see the effect of a groin. Accretion on one side and erosion on the other. Build one, build the next one even further out. Again, you're trying to change the average direction so that you have a buildup on the incoming side of the longshore drift as it hits that unnatural perpendicular structure. Of course, it's really important to protect up here. Probably it has some sort of shopping mall on it or something like Atlantic City. Let's put a groin at the end. And over time, what do? We can even put a breakwater. Happy community, unhappy community. Remember, as soon as one goes up, multiple will appear. Again, groin field. This is all built up. So they're trying to protect themselves. This is probably some sort of part of a national seashore or national wildlife area or something that doesn't allow man-made manipulation. And look what happens. Massive erosion. This is what happens all along Fire Island National Seashore. You have groins in Ocean Beach and in areas where people live, where there's infrastructure. And then as soon as you hit the Fire Island National Seashore, like Sunken Forest on the opposite side, this is the erosion you're going to experience. Again, really important to protect a Ferris wheel and a parking lot right at an edge of where an inlet's going to be. But look at that beautiful, wide, flat beach that we can collect money on. Opposite side, though, if you live this way, you're in a lot of trouble. Another example of accretion on one side, erosion on the other. Bulkheads do the same thing. So instead of going perpendicular to shore, they go parallel to shore. And remember, the waves are going to come in and drop, come in and drop, come in and drop. So the further away the bulkhead is, the wider your beach. But ultimately, over time, in a bad storm, all of this sand is gone. And all you'll have left is that bulkhead, which will function as a seawall. Rock revetments, again, a whole bunch of different rocks, big and small, sometimes in wire baskets, sometimes just placed. Sometimes you'll see them as geotubes. This is the same location on Long Island, South Shore. Look how wide this beach is. That's after they buried the material, covered over it. But over time, allow there to be a storm, this will be all lost. And we're right back to where we were left off with absolutely no beach in front. Beach scraping, of course, functions like this, wide and flat. You put a pile and you drop it on. Most importantly is to try to let the beaches help themselves. Anytime you see a sign that says stay off the dunes, it's not because we don't want you walking across that particular part of the beach just because. You'll notice that all of this grass, that's a natural vegetation, it has roots. Those roots, like your hair, go deep. They run long, right? What do? Well, if you have lots of roots overlaying each other, like a lattice work, what do during a storm or during wind? They literally trap the sand. So as the sand gets pushed on the beach and the wind blows during a storm, the sand from the beach literally gets stuck in the hairs of the grasses, and the dune ultimately grows in height. When left alone, dunes can be 20+ feet high. Unfortunately, when you trample on them, you have a really, really, really large impact. At the end, ultimately, the purpose and our goal for all of this is not to have a shoreline that looks like this, but instead, and that's in Jersey, really close to home, but instead to have a shoreline filled with beach grass so that we can have the very first picture of our natural beach, and we can continue to have wide, flat, sandy beaches with natural protection, which ultimately protect all of Long Island. And that's the end of the Coasts and Beaches lecture.